Hello, welcome back to ECE484. My name is Chris. Hopefully everything is going okay in terms of the lab and so on. Everything's sorted out. And last Friday I posted the first tutorial, also the second problem set for you guys to practice. Okay, and solutions were also posted to the first problem set in case you wanted to check your work. Okay, so what did we do last week? We've been talking about the time domain response of systems, and we started focusing on the transient response, so the part of the response which eventually goes away. And it's convenient to focus or assume that the plant is a second order system because it allows us to directly relate pole locations to some of the characteristics of that transient response. Okay? And so we focused on this prototype second order system written or parameterized in this funny way with k, where k is a steady state gain, omega n is the undamped natural frequency, and so on. And so we basically categorized the second order systems based on their pole locations. And when this damping ratio is between 0 and 1, you get complex conjugate poles, and that system is called underdamped. And dynamically, it's the most interesting situation because it exhibits overshoot, oscillation, something that none of the other kind of categories of second order systems can, and nor can a first order system. Okay? And so here we had the pole locations for a second order system, kind of a picture we drew last time. Okay? And we basically stated some formulas for some of those characteristics. So, and what we saw was that the settling time depended on the real part of the poles, the overshoot depended on the argument or angle of the poles, damping ratio, and the time to peak depended on the imaginary part of the poles. Okay? Okay, then we moved on to sort of the other kind of type of input. So not a step input, but rather a sinusoidal input, and that led us to the notion of a frequency response. And the hallmark of a linear system is that whatever frequency you put in, you get the same frequency out. But the difference, or what the system can do, is it can change the amplitude and the phase of the steady state output. Okay? And so that motivated us to call the transfer function, when you replace s with j omega. Oops. Sorry, I think I have a technical issue here. 1 second. Sorry, 1 moment. There we go. That motivated us to call the function g of j omega, which is the Laplace transform, or the transfer function g with s replaced with j omega. So in other words, restrict s to be on the imaginary axis. We called that the frequency response of the system. Okay? And we gave an example last time where we used the frequency response to compute the steady state output due to a particular input. Okay, so we're going to continue from there. And so, it's convenient to graphically represent that frequency response, because instead of doing what we did last time where you take the input, you figure out the particular amplitude at that input and the phase at that input, you just kind of look it up on a graph, right? It's a nice simple way to see all the information. Okay, and I'll remind you that Bode plots are a graphical representation of the frequency response. Except that the axes are kind of expressed in funny units, right? So you have the magnitude Bode plot, which is written in decibels. So you don't write the vertical axis in just a magnitude of g of j omega. You write it in this funny unit, decibels, and typically log. You use a log scale for the the frequency, okay, base 10. And there's a phase Bode plot, and that is typically just the angle in degrees, also with a log scale for the frequency. Okay. Now, in previous courses, you might have spent a bit of time trying to figure out how to plot these things by hand. I'm certainly not going to do that in this course. For the most part, we'll use MATLAB to draw our Bode plots, but it's important to know what information they contain, right? And they contain information about the frequency response. All right, let's do an example. So again, the numbering indicates this is an example from the notes. Okay, and so the system that we're going to consider is just an RC circuit. Okay, so here's my drawing of a circuit. Let's call this C for capacitance, R for resistance. The input is the applied voltage. The output is the voltage across the capacitor. Okay, so you can verify that the transfer function for this guy is given by 1 over RC over S plus 1 over RC. Okay, and let's just assume, because I want to draw a frequency response, let's put some numerical values in there, and let's assume that RC, that product equals 10 to the negative 1. Okay, so then if that's the case, we get a very simple transfer function, right? 10 over S plus 10. Okay, so the frequency response is you just set S equal to j omega. So the frequency response in this case is that guy. And then you could draw your Bode plot. Okay, again, I won't review how you go drawing these things by hand, but I'll just draw kind of an asymptotic Bode plot. And if you remember, that's great. If you don't, it's not such a big deal. But okay, so let's draw the Bode plot for this guy. So this will be my magnitude plot. So log omega, 20 log of g of j omega, and then I'll do my phase down here. Let's just copy that. Okay, oops. Something like that. Okay, so this will be my phase. In degrees. Okay, so again, if you don't remember, that's okay, but one thing you might remember is that the pole location, and 0 in general, in this case there's just a pole, tells you something like something starts happening at the Bode plot at that location. And so in this case, that pole, let's put some numbers here. Let's call that 0, 1, 2. Right, so 0 on a log scale is omega equal to 1, 1 is omega equal to 10, 2 is omega equal to 100. So the pole location is at 10, so here's our pole location. Okay, so 0, 1, 2. And so what happens is at low frequencies for this guy, you see that the magnitude is approximately 1, right? You get 10 over 10 because the value of omega is small. And so our asymptotic plot would look something like this. Right? The magnitude is 1, which on a dB scale, that gets mapped to 0. And then after the pole location, sort of the pole kicks in and you get this attenuation, high frequency attenuation. So we'll draw this way. Right, so the slope is -20 there. All right, and so the phase does kind of something like that. So it's going to be, for small values of omega, you see that you're just basically taking the angle of a real number, right? G of j omega is approximately 1. And so the angle of a positive real number is 0. And then for large values of omega, you see that you're basically taking the angle of negative j omega, or 1 over j omega. And so that's a negative 90 degrees. And then you do linear interpolation in between, and you get your asymptotic Bode plot. Okay, so this is -45. Okay, so this is the asymptotic. This is called the asymptotic Bode plot. Asymptotic because it's not the exact value, right? If you drew this in MATLAB, it wouldn't give you such nice lines like this, but roughly speaking, it's close to what you would see in MATLAB. Let's make some observations, right? The point here is, if you remember how to draw them, great. If you don't, it's not a big deal. But let's use this figure to make some observations. So at low frequencies, this circuit is going to let the output, the amplitude of the output will be approximately equal to the amplitude of the input, right? You see that on the magnitude plot, you're at 0 dB for low frequencies. So at low frequencies, our magnitude response is approximately equal to 1. And so if you apply an input at low frequencies, the output, won't lose much power. It'll have almost the same amplitude. Okay? But there's sort of this breaking point at 10 radians per second where it now starts to attenuate, right? High frequency inputs, they start to basically not show up at the output, right? Their amplitude starts to get really small really quickly. Okay? And so what we say for this system is that it allows signals to sort of pass through, so inputs to appear at the output up to about 10 radians per second, and then after that, it starts to cut them off. And so in the terminology you may have heard before, we would say that this system has a bandwidth of this system is 0 to 10 rads per second. Right, so the width of that interval is 10, so you'd say that the bandwidth is 10 radians per second. And the idea being that anything in that range shows up in some sense at the output, anything outside of that range is heavily attenuated. And so if you want a more formal definition, I'll point you to a definition from the notes. Okay. The point being, it's easy to read off a Bode plot, right? You just go in for a low pass kind of system like this, you look at the low frequency gain, which in this case is 1, and then you figure out the frequency where it drops 3 dB. And so for our asymptotic Bode plot, that's exactly at the pole location. Okay, inputs with frequency outside of the bandwidth. Or frequency above 10 radians per second. Produce outputs whose amplitude is heavily attenuated. Okay. All right. Will we be using MATLAB for the midterms exams? I can't stop you, so yes, if you want, you can use MATLAB. It would be unfair. If I were to say no, how could I stop you, right? So It won't help you so much though, I don't think. But yes, you can use it. All right. Let's move on to we're almost done chapter 2, so my hope is to finish chapter 2 today and we get the new material tomorrow. But okay, let's talk about dominant poles and zeros. In our time domain section, 2.5, we assumed that the system was second order. So in section 2.5, in particular 252, we derived formulas for second order systems. Right? But most systems are not second order, right? So, well, okay, let's say that. However, our formulas for higher order systems are hard to obtain. Okay, and most systems are not most systems are going to be, if they're reasonably complicated, they're going to be higher than second order. Okay, so what do? Well, if you remember back to our motor example, sometimes a system has sort of a natural time scale separation, right? There's sort of a fast part of a system dynamics, and then there's a slow part of a system dynamics. And again, we saw this when we looked at the DC motor. However, sometimes systems have a natural timescale separation. Example, as we saw before, the dynamics of an electrical subsystem are faster than the dynamics of the mechanical subsystem. Okay? And so when you have these sort of natural timescale separations based on the physics of the system, how does that manifest itself in terms of a transfer function? Well, what it means is if you look at the poles and zeros of the plant, there's going to be some that are closer to the imaginary axis and some that are further away. The ones closer to the imaginary axis sort of represent the slow dynamics. The ones further away represent the kind of the fast dynamics. So these timescale separations result in some poles and zeros being closer to the imaginary axis. All right, so let's draw a little picture here. Okay, so there's the real part of S, there's the imaginary part of S, so our complex plane. And what I mean by this is that you might have some poles here which are close to the imaginary axis, and then you might have a group which are relatively speaking, further away. Okay. Well, it turns out that for low frequency inputs, like step inputs, the response, or what you observe in the response, the transient part of the response at least, is going to be dominated by these slow poles and zeros. So for low frequency inputs, like steps, the transient response due to poles and zeros far to the left dies off quickly. Right? In other words, in a short amount of time, you won't see what's happening. And so let's do a little mini example. So e.g., I'll give a rule of thumb of what I mean by far to the left, but look at this transfer function. It has a pole at s equal to -1, pretty close to the imaginary axis. It has another pole at s equal to -10. Let's call that relatively far away. And let's look at the step response of a system with this transfer function. So here's the unit step response. Y is the output signal, G is the transfer function, and 1 over S is the Laplace transform of a step. Okay, well, if you go back into the time domain, use your partial fraction expansions, whatever the case, whatever you like to do, go back into the time domain. What is the response going to look like? It's going to look like C1 plus C2. Oh, that's right in the time domain. Okay, sorry. Let me do the partial fraction expansion. Won't skip a step. If you do a partial fraction expansion, what is this going to look like? It's going to look like C1 over S plus C2 over S plus 1 plus C3 over S plus 10 for appropriate constants. We know C1 from the final value theorem, it's G of 0, but C2 and C3, you got to do some work to calculate it. Okay? Go back to the time domain. And what do we observe? Well, let's look at this, right? The pole far to the left, the pole at s equal to -10, is producing this term here. And that's going to very quickly die away, at least in comparison to the pole which is closer to the origin, or the imaginary axis, which has this -1 decaying exponent, right? E to the -t. And so in some sense, if we were to neglect this in the step response, it wouldn't be perfect, but probably reasonably accurate. Right? You're not going to really easily be able to observe this 10 to the -10, e to the -10t term, depending on the time scale you're looking at. But for for most kind of robotics or kind of electromechanical applications. Okay, so that's the basic idea. What we'll do then is we'll take these poles and zeros which are far to the left, and we're going to replace them with just their steady state effect, the effect which remains over time, and sort of ignore their effect on the transient. And what's that going to do? It's going to take the order of our transfer function, it's going to reduce it. We're going to get a lower order model. And if we're lucky, that lower order model is going to be second order, and we can use all the formulas that we had from before. Okay? So we can reduce the order of the model by replacing quote-unquote fast poles and zeros with their steady state gain. All right. So let's do an example of this, and then we'll move on. This is example 271. Okay, so the example is meant to show model reduction, so reducing the order of the transfer function g. So g in this case, let's write it out. Okay, so there's our g of s. Okay, so let's plot the poles and zeros of this transfer function and see if there's sort of what we would call the dominant ones for the low frequency input. Fast poles are close to the imaginary. So no, those would be the slow poles. The slow poles would be, so if you go back to our little mini example here, so let me draw this to sort of illustrate it. So here, I'm kind of running out of space, but if I were to draw the poles of this guy, you had one at -1 and one at -10. Hopefully you can see that. And so the pole at -1, I would call slow because it takes longer for its transient response to go away. Right? Whereas the pole at -10, it decays very quickly to 0. So I would call that fast, right? Its transient goes away quickly. So let's call that fast. Whereas the slower one kind of is a bit more sluggish. Its effect lingers over a longer period of time. Okay, so let's draw the poles and zeros here. Oops. And so for this guy, we have obviously poles at -12, -11. This is not to scale, okay? A 0 at -10. Okay. And then we have those roots of that second order polynomial, which are going to be complex conjugate. And they are at, let's see, -1 plus or minus j. So -1, 1, -1. Okay, so as to, kind of repeating the question, we're going to call these the fast or non-dominant, and we'll call these the slow or the dominant poles. And so the terminology you might also see are these are the non-dominant and these are the dominant. Okay? And so the idea is we're going to factor the transfer function into the fast part, or the non-dominant part, and the slow part, or the dominant part. Okay, so let's write this as so that's what we're going to call the fast part. Let's G subscript fast. And then what's left is what we'll call the slow part. So times 1 over. Okay, let's call that G slow. Okay, and so the idea here in our model reduction is we'll take that, because assuming we're interested in a step response, right? If you're interested in frequency response at other frequencies, you might have to consider fast. But for step responses, as we saw above, that fast part's going to decay quickly to 0. Okay, so we're going to replace it with its steady state value. So let me write that down. For low frequency inputs, G fast of S approaches its steady state gain, remember final value theorem, G fast of 0, quickly. Compared to G slow. Okay, And so what we'll do is we'll take our model and replace g fast with that g fast of 0, or steady state gain. So which in this case is 10 over 132. And we let g hat be sort of our approximation of g. So g hat will be g fast of 0 times g slow of s, which in this case is 10 over 132. Times what's left. Okay. And so then now you could go and you could look at the step response of g hat and compare it to the step response of the original g. I think I do this in the notes. And you see they're going to be very similar, right? There'll be small differences, but not very noticeable. If you look at the Bode plot of g hat compared to the Bode plot of g, for low frequencies, they'll be very similar. At higher frequencies, once you start kind of getting to these poles and zeros, they'll start to differ. So the Bode plots will be different, but only at higher frequencies corresponding to these poles and zeros. So the Bode plot of g hat is similar to g's at low frequencies. Sort of indicating that they're producing similar outputs at those frequencies. Okay, fine, that's a specific example. Let's generate a rule of thumb. Like what can we reasonably expect these timescale separations? And of course, this is a rule of thumb, right? It's very much application dependent on what you need, but a rule of thumb, a good rule of thumb, is if you've got like a 5 times difference. Let me draw a picture and then explain the rule of thumb. Okay, so suppose that you've got a system that looks like this, 0. Right, so we've got some poles close to the imaginary axis, and then you've got this other group over here. Okay? And let's say that this line here in the sand let's say that that's some, it crosses the real line at some value. Let's call it negative sigma. Right? So negative sigma is where it crosses the real line. We're going to say that we can neglect fast poles and zeros if they're 5 times further away from the imaginary axis. So in this picture, what we want to say is that that line in the sand over there, negative 5 sigma. Where did I get 132 from? Oh, did I make a mistake? 11 times 12? Yeah, that's right. 11 times 12. Right, so g fast, this is g fast. Sub in s equal to 0. The numerator is 10, and the denominator is 11 times 12. Okay, so slow for us. So slow or fast means at least 5 times further away. From imaginary axis. Okay? So it's a rule of thumb, of course, it depends on the application, but that's a reasonable rule of thumb. And so again, in this picture, this group over here is 5 times further away than this group over here. Okay. So the very last thing we're going to talk about is kind of a very nice idea from control theory, one that you've seen before, but remind you again. So that is, we're going to talk about tracking. So we'll start with step inputs, and then we'll generalize to any reference signal. Okay, so the picture, let's see if I can do this. Okay, so the picture, bear with me for a second. This picture is our usual setup. Okay, so controller, plant, disturbance, and so on. And the step tracking problem is we want to design the controller C so that we get, obviously, stability, goes without saying, closed loop stability, but also we want that the output Y asymptotically track constant inputs, constant reference inputs. Okay, and so that's the problem. To provide I/O stability and such that our tracking error goes to 0. For step inputs. So we write down and then we'll okay, so what is the problem asking? We want to design a controller, C of S, so that we have stability, and furthermore, in the limit, as time gets large, the reference, or the output Y, converges to the command signal reference R, and that difference goes to 0. In other words, the tracking error E of t in the picture above goes to 0 for any size of input, right? You can imagine, think of a thermostat, right? You go to, you come to school, temperature in the winter, temperature goes down. So the constant value that you're tracking goes down, right? You get home, the constant jumps back up, it's a different value of R0. You go to sleep, maybe it drops again, right? So there's this, if you were to plot the reference signal for a thermostat over a day, you would get this, a bunch of step inputs, right? Sequence of steps of different values. Okay, so that's why I leave it as R0 as a parameter. R0 could be any number depending on what the user sets in their thermostat. Okay, and when the disturbance is 0. Actually, the controller we're going to design would work when the disturbance is constant as well, but let's just assume for now that the disturbance is 0. Okay, so the transfer function, as we saw before, from the reference to the tracking error is given by 1 over 1 plus Cp. Okay, and the Laplace transform of our reference is R0 over S. Okay, so that's the setup we're going to look at, and we want to figure out when does that error go to 0. Okay, so assume the controller provides stability for now. So assume for now that C stabilizes the loop. And let's apply the final value theorem. Or let's see if we can apply the final value theorem. So we have that the steady state error which is the limit, what does, oh, ST, such that, okay, let me see. And such that, let's write it out. That's probably not a good. And such that. Okay, so our steady state tracking error, limit as t goes to infinity of the tracking error is going to be equal to, if final, let's put a question mark here because I'm not sure that the final value theorem can be applied. So let's go back and, afterwards, let's make sure that this equal sign that I wrote there is actually permitted. So if the conditions of the final value theorem apply, then that's what I would have, right? It all depends on whether or not S times capital E, whether that signal or that Laplace transform has any bad poles, right? If it has no bad poles, we're good. Okay, so let's go through the calculations. Limit as S goes to 0 of S times. Okay, there's our transfer function, and there's the Laplace transform of the reference. Keep going. I'll pull out the R naught out of the limit because it doesn't depend on R naught. The S terms are going to cancel, so let's get rid of those terms. And then let's do what we did before and write everything over a common denominator. And so what we will get is the denominator of the plant, denominator of the controller, over our characteristic polynomial, right? That's the transfer function we saw a while ago. Okay, remember we assumed that C stabilized the loop, and we know that the loop is stable if and only if the characteristic polynomial is Hurwitz, i.e. has all its roots with negative real part. So this guy is Hurwitz by the assumption of closed loop stability. Okay, so in particular what that means is that I can get rid of this question mark. Right? Indeed, final value theorem did work in this case. Okay, but we want that to be 0. We want that steady state value to be 0. And so you immediately see that the only way that that's going to be 0 is if when I plug in S equal to 0 in that numerator, I get 0. So we get that the steady state tracking error equals 0. In other words, our room temperature reaches what the value that the thermostat, what you programmed into your thermostat, if and only if that numerator goes to 0. So what does that mean? It means that the plant or the controller has to have a pole at the origin. Integration, right? You need an integrator. You surely remember this. If you want step tracking, you need integration, and this is why, right? The final value theorem tells you that the only way it's going to work is if either the plant has a pole at the origin or the controller has a pole at the origin. Integration. Okay, so that tells you, this gives you a design strategy, right? If you've got a plant and your spec is perfect step tracking, this gives you a design paradigm or a design cases. So design here, we're talking about step tracking. You want to solve the step tracking problem. So if P has a pole at s equal to 0, and you want perfect step tracking, the controller just has to stabilize the loop. Okay, so that's the easiest kind of case in some sense. 2, if P has a 0 at s equal to 0, well, we're screwed at that point. We cannot add integration, because if we do, we're going to get an unstable pole zero cancellation, and we will not have stability. So we cannot, there's nothing we can do in this case. So asymptotic. Step tracking, not possible. Okay, because again, the only way that we're going to get that product dp dc to equal 0 when s equal to 0 is by doing a cancellation. We have to cancel the pole the 0 that the plant has, and then add another one. Well, as soon as we do that cancellation, we've lost stability. 3, if the plant has neither a pole nor a 0 at s equal to 0, then the controller has to provide the integral action. So what do? You pick a controller of the following form. So you add the integral, right, the pole at the origin, and then you have this other part that needs to be designed or chosen, C1. And the role of C1 now is just to stabilize. So 1 over s kind of provides the integration, and C1 is the stabilizer. And then design C1. To stabilize the loop. All right. Okay, so integral control needed for step tracking. We can generalize this. I'll make the statement, and then I'll kind of, next class, I guess I'll have to finish it. So let's generalize what we just saw for step tracking. The so-called internal model principle. Beautiful idea. Stabilized loop, I mean the same thing. So I mean what we talked about earlier, input-output stability, feedback stability. Every possible transfer function associated with the closed loop system has to be Bibo stable. The same thing we talked about last week. That we have only one definition of a closed loop system being stable, right? Okay, so the internal model principle is beautiful. Basically, it says that any good controller should have a model of what you're trying to track. And I'm going to run out of time, so probably won't be able to write it, but so let me just make the comment. It's basically saying that if you want something to track, the controller should have a model of the thing it's trying to track inside of it. Okay? And the analogy I give is sort of like if you're skilled at, say, fixing a bike, right? Someone gives you a bike which is broken. A skilled person, someone who's really skilled at doing something, they have in their mind what a functioning bike looks like, right? They look at the bike, they identify the problem, and then they know they have a model of a correct bike in their mind, and they use that model to guide their repair, right? Someone who's not skilled, well, they'll put on a YouTube video and they'll follow some step-by-step instructions, kind of without understanding what's going on. they don't have a proper internal model of what a functioning bike is working. And so the internal model principle is sort of the control theory version of this. And I've run out of time, but I'll state it next time. And basically it generalizes what we just saw for step tracking to arbitrary reference signals. Okay, I'll stop there. I'll hang around for a couple of minutes if you have questions. Otherwise, I will see you tomorrow.